wire in it would be 0.63 metres squared. All right. Now remember, it's only 40% open, so only 0.4 of that is actually open, so 0.25 square metres per metre length of screen. That's very easy, of course. There's our open length, that's what we've got per metre. We're going to need about 7 metres of screen to achieve that safe velocity. Okay? Probably add a bit more than that, bung about 10, and depends how much money you got. You could be really good there, 20, it wouldn't really matter. Depends how deep you want to drill your hole, how deep you drill it. But either way, you've got to make sure that these calculations are done. One, the velocity within the casing, and two, the velocity through the screens. Simple stuff, there's reasons for it. If you don't get it right, then things won't go well in the long term. In fact, they might not even go well in the short term, and you don't want either of those because you have a job. There's the screens, okay, instead of those continuously wire screens. Reasonably large opening in these ones. This is for sort of very coarse materials down in Taranaki. But anyway, on site, like I say, when you go and check all the other stuff out, you go and check the screens as well, make sure they're the right material. Like stainless steel, or should be stainless steel. Okay, you can check the slot widths. Okay, they'll have a specification that goes with them, same as the pipe did before. Okay, and you look at the assembly of the thing as well, and you actually watch them put all this together to make sure that it's all done properly, and they don't just show you the bits and then replace them with cheaper nasty bits later on. You'll do lots of site checks during this part of the investigation. Okay, you can on site quite a bit. You know, check that things are going along with those that you've stipulated in the contract. Take a shoot on that. Okay, construct the well. Right, we've told them what size casing we want, we've told them what size screens we want, we've given them lengths, we've given them instructions on how to construct it. The pipe will be welded together with fully penetrating welds, full circumference, normally 3 passes, etc., etc., etc. And so now give them the design, and they want materials, and they start. In fact, a lot of the time they'll have materials already because they'll have preempted the fact that this is going to happen. If not, then they'll use them on another job later on. So you drill a big hole this time, okay, down to the depth of where you want to put your casing. This time you won't core it, it'll just be a big roller bit, okay, a 300mm diameter roller bit, okay, on the end of a very large drill rig that'll just pummel its way down into the ground, hopefully pretty quickly, and just cleaning up material as you go. You don't need to look at the material that comes out, you already know what's there, okay, you've already drilled the pilot bore. See, well, this is just making a big hole straight down into the ground. You'll install the casings, you can align it, weld it together, lower it to the hole where it's the right depth. Check its alignment and its plumbness, make sure it's straight, make sure there's no kinks and bends in it, things that looks like the pump going down. Right, then you'll route the thing on the hole, cement it in. Continue drilling through the casing, down to the depth you'll put the screens in. And there you put your screens down into the hole, finish everything off. Develop it, clean it all out, get all that filter cake off, all that nasty smeared stuff that's been smeared against the aquifer while you've been drilling. Okay, you'll pump all that out, hopefully. Disinfect it, and then you'll just leave it until the next stage, which will be the pump testing. That's when you get a different contractor comes along and puts things in the hole and extracts water through varying means. So it's very not that anything else. It gives you data which you then analyse. But you need to like I say, visit the site a lot during this particular process. I talked about that in the contract, so there are stop points and hold points and all sorts of other things. Before and during the casing installation, you want to check the casing, but you also want to make sure they're putting it in properly. Okay? You want to do things like check the welds, check that they're aligning it correctly, etc., etc., etc. Okay? Check it conforms to specification as well. You also want to observe them grouting it in to make sure they are doing it properly, and the grout fully returns to the surface, so you've got maximum protection between the casing and the ground, and also maximum strength keeping you well open as well. Before and during the screens go in, you'll need to be there as well to make sure everything's all good, and you'll check welds, etc. for that as well. Okay, so there's a lot of practical stuff that goes on here as well, which you have to be present for. Now, it can be a real pain in the butt. There's one bloody case we had with the drillers. They ordered their casing right on site, and it hadn't been beveled. The manufacturer hadn't beveled the ends of the casing, which I'll talk about in a minute. And so we're already flying down to New Plymouth to go and check on the casing and the installation, because they were going to build the well on the site so we could see it. And you get phone calls 8 in the morning saying, oh, it's not going to happen. So you're going to go, fair enough. So you cancel all your bookings and your flights. And then they said, oh, it'll be a couple of days. And then 4 o'clock in the afternoon, they said, we're ready to go. And you go, then, yeah. And so then you've got to rebook your flights and your accommodation and get to the airport and get down to New Plymouth before everything closes and try and find McDonald's and hop in a rental car and race out to the site which you've never been to before. It's 8 o'clock at night and it's pissing with rain, pitch black in the middle of winter. It's great fun. Everything that can possibly go wrong will go wrong on at least one job. And this was one of the ones that went wrong on. They did the job really well, but they've got to give this a little time. Yeah, it's good fun. Just be prepared for those kinds of things. Okay, so the drill rig, much bigger than you were using previously. You know, the last one, I think, what was it? They did have about 2-3 metre lengths, so they get about 6 metres of rods above the ground. These things here are like 12 to 18, 20 metres high. They're big trucks, lots of grunt, very noisy, big smelly old diesel things. But they're the ones that you use for putting the big holes into the ground. You can see there's the driller, and there's the length of rods that they're using. All the heavy gear. Okay, the heaviness is great because it keeps everything vertical, going straight down into the ground. But you need a lot of power to turn it, a lot of grunt in these things. Everything when you're building wells is bigger. The mud pits are huge, so everything's big. And it's more than a two-person operation. When drilling the pilot bores, 2 people is enough to run everything here. You've got 3 or 4. So if someone's standing up here and feeding the pipe across, you've got the driller and the other workers down the bottom with all the tools and everything grunting away. But it usually goes pretty quick because if you need a decent rock in, you've got to drill. But that's what he's doing because these things are they're pretty grunty. It's all good. Big mud pits. Okay, don't go near those. They're really slippery. They use really, really, really slippery stuff. A lot of it nowadays is polymers. It's all man-made, and it's really, really slippery stuff. You don't have to go, you get much on the bottom of your boots to go for a skate. You don't want to go near those. All various things here. They'll mix the grout in these things before they pour it down the hole to cement the casing and some bags of cement, all sorts of things over the place. But again, it should be a tidy workplace. Everything should be contained within boundaries. It should all be fenced off, in fact, for safety. Public aren't allowed on there to just to wander in and have a look around. All those sort of things that OSH necessitates nowadays. You have to wear bloody hard hats and vests and things. Hard hats are actually a waste of time. The only thing they're good for is to stop you banging your head on things. Otherwise, they're actually not really that useful for much. Anything going a reasonable velocity or a reasonable weight will go through it to crank your head anyway. But you have to wear them. Oh. So all the gear's big here as well. Okay? Big long drill rods, big bits, all the reamers and openers and things at the back. Heavy bits. Okay, so you need all that. Okay, because A, you've got a big diameter holes, and B, they've got to be vertical. They've got to be plumb. Okay, as the weight on the drill string will keep that happening. By the time you get down to about 200 metres with all this gear hanging on the end, okay, the drill rig is holding up several tonnes of steel as it goes down into the hole. So it's why it's so big and grunty, but it's doing its job by keeping everything nice and straight. Okay, so they'll weld they should weld anyway. You've got to line the casing, okay? The casing has to fit together perfectly, edge to edge with no overlap, on the inside, so that when you put things down the inside, like the screens and the pump doesn't get caught up in the casing, which would be an absolute disaster. So they should weld little alignment tabs on to one end of each piece of casing, and then they'll lift the casing down and set one piece on top of the other. And of course, those alignment tabs on the piece they're setting down will fit perfectly over the piece of casing that they're holding up here in the hole in the grips. And then it's just a simple matter of welding this here to weld it all together. So when they sit the casing together, see these beveled edges here, leave a nice recess all the way around here. Okay, when they've finished welding it up, that should be nicely filled all the way around. Okay, so you don't get any leakage, nothing can get in, nothing can get out. The welds must not penetrate inside the weld for the same reason as the casing can't overlap. It's a very simple process, okay? They'll be very experienced at doing it, but you've still got to check that they're doing it properly. Okay, so it's very important. Then they, of course, lower this one down, they knock the tabs off, just come off with a hammer, lower the next one down, and put another one on top, and it's just a process. So it actually happens reasonably quickly when you've got an experienced team that know what they're doing. Once your casing's sitting on the bottom of the hole, they'll weld a flange onto it there, which you can bolt a cover onto it, or do whatever you want to keep the weld safe later on. But you notice between the casing and the edge of the hole is quite a sizable annulus. Okay? At the very top of the hole it's big, because first they put in, they call ductor casing, they drill a big hole a few metres deep, it's really wide, they work everything in below that, and the annulus won't be as big. But this is what's going to be filled with the cement, okay, to keep that well upright, to keep the aquifer material, sorry, the rock and everything from interfering with the metal, okay, to keep everything strong. They've got to test the plumbness and alignment of the thing to make sure that you can get a pump down there, you can get screens down there and in and out, okay? And so they'll make up some sort of dolly, which is generally, it'll generally be the length of, it depends how they do it, But if you're doing a solid one like this, it's got to be the length, half the length of casing, okay, so it can slide through quite easily, and it should go all the way from the top of the hole to the bottom of the hole without interference, okay, and that'll mean that your well is nice and unobstructed. What they'll also do is an alignment test as they lower this down with the little device they sit over the top here, and the cable rests against it. If at any time the well deviates from vertical, then the cable will move against here, right? And you can note that. And if it gets excessive, they may have to do something about that. Basically, as long as their dolly goes from top to the bottom of the well, it should be pretty safe. Well, it does help if the well is vertical and not tilted at any angle, because of course then when you put a pump down, it's going to slide against the side. You want the pump to hang in the well at depth. So the plumbness is very important, as is the alignment. They should test that, okay, and again that will be written into the contract. They'll have to give you the methodology as to how they're going to do it, but it'll be written in there. Right, grouting the casing in. Now this is that one I was talking about in the middle of the bloody night, up there at 1 o'clock in the morning. Still grouting the sodding casing in. Still would be night music too. They mix the grout on site sometimes. Depends if the site's easy to get to and it's normal work hours, they may actually just chuck in concrete already mixed, already pre-mixed. But often they'll mix it on site. Okay, they've calculated the approximate volume they need. They know all about this. They know the consistency. They know what the final grout needs to be like. And so they'll mix it on site, and they'll basically the casing is sitting here on the bottom. They pump the grout down to the bottom of the casing. Okay, so the casing, the inside of the casing is the grout. That sounds weird, but that's how you do it. Chucking water on top, seal it up. Then you pressurise the water. Okay, and the water will push downwards and will push the grout up and downwards and up the outside of the casing. And it should come somewhere near to the surface by the time they finish. That's one thing you have to make sure of as well. They can finish the rest of it off when they do the weld head later on. So basically they'll lift the casing off the bottom, pressure that into the part of the casing, and the water will push the grout down and up the sides. And isolates it from the ground if everything's done properly. So you've got a nice annulus around your casing. Okay. Then the screens go in. Okay, you've looked at the screens, so you can see we're putting an awful lot of screen into this well. This is the vast amount. This was down on, yeah, this is that same Taranaki joint as well. This is daylight we've got. Basically, you then drill through the middle of your casing, so you lower the drill string down through your casing at a narrow diameter, carry the hole down to the depth you want it to, right, weld your screens together, install various assemblies on it. You've got this J-latch, this is how they lift the thing up and down. Okay, and the crossbar goes down, hooks into that, pulls up and down. You've got this rubber packer here, which will seal the screens against the inside of the casing, down the bottom of the casing, okay, so keeping everything integral as we had before. And you'll get a sump. They'll load it, they'll weld a sump on at the base, so 1 or 2 metre long hollow tube that will catch anything, hopefully, that falls into the well so it doesn't get up through the pump, and it'll also support the well on the bottom, so your J-latch and your packer and your sump. Then they'll just finish it. They'll top up the concrete if they need, top up the grout, make a nice concrete pad, okay, on the surface, keeping everything nice and tidy. Okay. The well will be developed. Remember for the previous one, the pilot bore, we had to airlift it, pull the water out, so the water from the aquifer went in through the sides of the aquifer to clean out material that had been smeared against the side of the well as you drill to remove it filtrate. You need that, okay, it makes your well more efficient, increases the productivity, also cleans the fines out of the well too, so you develop it. You can airlift it. The more common in these big ones, you'll probably jet that you load one of these things down, and high pressure water jets out these holes, okay, and they'll gradually move it up and down through the screens and spin it around, so the water will jet through the screens, hit the aquifer, loosen all this material, which will then wash the aquifer. They'll airlift at the same time and suck all that nasty water out. Sometimes they'll surge it, they'll put a surge block down. This thing's like almost like a plunger here, keeping your sink fixed again, except down inside the well. And they'll move it up and down, that forces water into and out of the aquifer. Again, having the effect of cleaning it out, and then you suck all the dirty water out through airlifting as well. It needs to be done for a long period of time. Remember the original one, a couple of hours until the water's really clear. This one here, you need to do it until the water is clear. Okay, the water has to be clear, and there has to be no sediment in the water, okay, or very, very, very tiny amounts of the stipulated amount that you can allow, but it's usually virtually nothing. Okay, when that's happened, you generally just shut everything down, chuck in some disinfectant, because nothing's going to happen to the well for a while. Okay, you're going to get pumping contractors in and all sorts to do things. Bolt on a cover and just go away. Right, so here's the process graphically. You've drilled your hole, okay, so it's uneven sides. Here's your water table, here's the aquifer that you're trying to tap into, here's the aquiclude, the aquitard above it, and all the stuff you want to case on. So basically your casing is going to completely fill this part of the hole. You want to isolate all of that from your aquifer. You don't want anything getting into your aquifer down below there, okay? So you put your casing down, lower it to the bottom, okay? Goes to the bottom. Remember, it's been welded together and aligned properly. Some alignment. Seal it up. Pump in the grout with that stuff they're mixing. That's the cement pump at the bottom. Chuck a slug of water on top of it, and yes, it will sit on top quite nicely. Okay, it won't mix. This will be at the bottom. Lift your casing a little bit off the bottom so that the grout can come up through here, and then pressurise this. The water gets pushed down, the grout gets pushed up the sides. Forms a nice seal here in the annulus, okay, keeps your casing isolated. You've got a really good well. It's done properly, you've got a well there that should last for a very, very long period of time. Then you just continue drilling down through the well and narrow down. So remember, this was 250mm casing, and we've got 200mm screens, okay, so you can through that down to the depth in the aquifer where you want to screen to, and lower your screens down, insert your screens. So that's the packer, it seals off everything against the side of the well. So this area of the aquifer is the only part that water will come from and through into your screens. Everything else is isolated there, it's all good. Sitting on its sump, there's the latch if they change it, if they need to grab it out again. And complete your pad, chuck a lid on it, and the driller's job is then done. That part of the contract is fulfilled, everyone's happy, hopefully they can go home. So after all that work, and all that time, all that investment, all that effort, that's what you get. That's all you see. That's it, right? After everything that you've gone through. Underground, of course, hopefully it's all well constructed, it's going to work properly, but that's all you get. So you can see why these things are really good. They're very unobtrusive, they take up very little space. You know, unlike a dam or whatever, okay, you've got a bit of an outlay, but nowhere near the cost, nowhere near the environmental effects, okay? Everything's all disappeared. Even when the whole project's finished, you'll only end up taking a very small area here where you'll have your power supply to your pump and whatever. You really won't see much in a completed well. It's a very, very small thing. It's not stuck in the middle of a road. We built this road especially for that. So, okay, I'll quickly start on this. It'll give me another 10 minutes because the next lecture is going to be extremely rushed. We probably won't finish it. Okay, once that's done, now you can test the thing. Okay, aquifer testing or pumping testing as it's more commonly referred to. To prove the long-term yield, accurately determine these so we can do our modelling. The contractor will be a different person probably than the driller. Okay, it's quite a specialty job, and they install a pump into the well, calibrate everything, and making sure that the pump can cope with the yield that we want it to get, etc., etc. They've got all the details that we've got there. Their experience, they know what they're doing here. You've got your pump well and observation bores. At the same time you've made the pump well, you've made more of those small bores like I talked about in the previous lecture, those obs bores or observation wells. You'll monitor those for a set period, generally about 24 hours before you start pumping, okay, just to see if atmospheric pressure or whatever affects your aquifer to any degree. See rainfall, is that affecting it to any degree, or is everything nice and smooth? Because you can use this for correction later. So rainfall, atmospheric pressure are also recorded. You establish the static water levels within the well, okay, so the piezometric surface within all these things are established. And then you conduct what's called a step test. Okay, so you pump well at increasing discharges for a set period of time, and from that, you monitor water levels and you graph that up, and you can get, you can get some detail from that, but you can get an idea of how your well will behave, and at least whether it's going to be able to cope with the pumping rate that you are asking the contractor to do. It's quite a useful thing to do. It doesn't take very long, and it's a sort of a day. That's quite an important step. Then you'll conduct a constant discharge test. You basically pump the well at a constant rate, hopefully the rate that you're hoping to achieve, for a long period of time, days, weeks, if possible. The longer the better, because you'll see the effects over a longer period of time, stretching out further, you'll get much better data. You monitor all the water levels and all holes that are available to you. Okay, you monitor the draw down. When you start pumping, you'll do this over a very short time interval, maybe 30 seconds. As the pumping duration increases, you'll go down to minutes, and then maybe only every hour until the pump test finishes. At the end of the test, you switch it off and you measure the recovery, because hopefully the well will start recovering as the water level recovers in aquifer, and you measure that as well for the same thing. And because you can use all this data from the step test, from the constant discharge test, in the recovery test, you can use all this data, right, to quantify your aquifer, and the more the better. So you get really good ideas of K, T, and S, which are really, really important because, say, your groundwater model is based on those values. Right, and you also visit the site during this particular period of operation as well, doing the pump testing. It's quite a different thing to what you've seen previously. Okay, no construction going on here. Here you actually don't see a lot at all, but you have to make sure you're doing it properly. So in the well, they'll put a pump of some description, okay, meeting the specification that you want. They'll put it reasonably deep down because, of course, when you start pumping, this water level drops, and once it reaches a certain level above the pump, it'll cut off. You don't want it to cut off. You want to keep pumping for a long, long time, hopefully ad infinitum. The pumps are pretty boring looking things. Okay, internally they've got a whole lot of these rotors. More rotors, if you want a greater pumping range, you just add more rotors. Okay, they're electric. The power cable and everything come out the top. They'll be connected to a riser. There'll be a pressure gauge and various valves up the top. But overall, you don't see a lot at the surface of a pump test. Okay, all the subsurface stuff is gone. It's all sealed off. You're not seeing it anymore. During the pump test, you'll monitor water levels. Okay, both in the pump well and in any odd spores you have. You probably won't do it manually unless you've got 3 or 4 people on site who will do it for you. If you're with your salt, you will have automatic equipment calibrated and suited in each well, okay, just constantly taking readings, and you know what time you start and stop things, so you know what data to use from your automatic recorders. Right. Yeah, this one as well. Cones of drawdown, pumping. What pumping does to the groundwater level around a well in aquifer. Okay, it makes quite dramatic changes to the groundwater regime, as you can understand. You're taking water out at a reasonable velocity. The closer you get to the well, the higher those velocities are. The bigger the faster the velocities, greater velocities, greater head drop, lower water level. So as the flow gets closer to the well, as soon as you turn the well on, you're taking water out of the ground, water starts flowing towards your well. Okay, that's the point, that's the place where the head is lowest. Remember, water flows from high head to low head. As it gets closer to the well, the velocity of the water increases. It has to. Here's your well, sucking water out of it. The water far away here, okay, it goes through, passes through a much larger area, a much larger cylinder. As it gets closer, each cylinder, the cylindrical area that the water has to pass through gets smaller and smaller and smaller. The same amount of water is going through, you pump at a constant rate, 50 litres a second. Right, so to start with, 50 litres a second has to go through this large surface area here. It goes quite slowly. 50 litres a second has to go through this smaller surface area here. Okay, later on, sorry, as it gets closer to the well, it speeds up. When it gets at the well, it reaches its maximum velocity, so it's going quite fast. Remember pressure, and hence I've got here H, decrease as velocity increases. Okay, and hydraulic gradient also increases as that velocity increases, as the pressure increases. Okay? As the pressure decreases, the velocity increases. So velocity, discharge over area, discharge is constant. As you decrease the area, getting closer to the well, the has to increase. Okay, it's just simple with the maths. Discharge, this KIA, Darcy's law, with discharge